Good morning. Welcome to this new day of Beyond. I am very pleased to introduce the first speaker today. She's going to talk on variational principle for Anosov representation, please.
Okay, so thank you very much for the introduction. And so in the fourth lecture, and I'm going to talk about the variational principle for Anosov representations. So my main goal is to prove the dimension formula for the limit sets of Anosov representations. And so let's just recall a few definitions. So the first one is Anosov representation. Oh, sorry. So we let gamma be a hyperbolic group. So for example, if you are not familiar with it, you can just take gamma to be the fundamental group of a closed surface of genus greater or equal than 2. And now I have a representation, say gamma to SL3R. So the representation is called an Anosov representation if we can find some constant C such that for any element in the group, and we take a look at the ratio between the first singular value and the second singular value, it grows exponentially with respect to the word length. And to continue, we consider the action of this rho gamma on this PR3. So the limit set of the group is the closure of the set of attracting fixed points of all the elements in the group. And so the main theorem I'm going to prove is this one. So again, so I take Anosov representation. So I require that this representation is Zariski dense. So the conclusion is that now we consider the limit set in PR3 and compute its Hausdorff dimension with respect to the Euclidean metric. So it equals the affinity exponent of the group. Okay, so this is the main theorem. And now let's just recall what we have proved and see where we are now. So, so we have this inequality. So the affinity exponent is greater or equal than the Hausdorff dimension of the limit set. So this is proved by Possetti, Sambarino, and Winhar. Okay. And to continue using the definition of the Hausdorff dimension of the measure, we know that this is, we have a lower bound. So take the Hausdorff dimension of the measure. So I can just restrict myself to stationary measures. Of some random walk, say mu such with, so the support of mu is in the group. Okay, and to continue, and we know that we can use the dimension formula for the stationary measures. So it's actually greater or equal than the soup of some nice stationary measures, and so the Lyapunov dimension of the measures. And so from here, we can see that to finish the proof of theorem 1, so we just need to bound this quantity below by the affinity exponent. And so this is what we call the variational principle. So let me write down the statement. So this is theorem 2. So this is a joint word with Yu Xiangjiao and Li and Xu and Pan. Okay. So more precisely, we describe in a quantitative way. So for every epsilon greater than 0, and we can find a finitely supported probability measure, say nu on this Anosov subgroup, and so I require that the group generated by the support is Zariski dense in this SL3R, and such that is unit station measure say mu on this PR3 satisfy that is Lyapunov dimension is greater or equal than the affinity exponent minus epsilon. Okay, so this is the two that go into this inequality. Okay, so now I want to recall the definition of the quantity that shows up in this inequality. So the first one is the Lyapunov dimension. Okay, and so it's defined as follows. And so we start with this Lyapunov exponents of the random walk, lambda 1 nu, lambda 2 nu, and lambda 3 nu. And so lambda I nu actually is to compute using the singular values of the random walk. So it's sigma I of the random walk, take the log, integrate, and divide by n. And now the Lyapunov dimension of the measure is defined using this formula. So if the first number entropy is less or equal than lambda 1 minus lambda 2, I use first number entropy divided by lambda 1 minus lambda 2. So otherwise, I do this formula, 1 plus this quantity. Okay? And the first number entropy is quite complicated. So I write down the formula. And let's just take a few seconds to digest the formula. As you can see, to compute the first number entropy, what I need to understand is that I need to push forward the station measure by some group element and compute the radium-Nicotium derivative. So as you can feel that, it should be a really hard to compute quantity. So that's why, in the first step, we are going to replace the first number entropy with an easier one. It's called the random walk entropy. And it's defined as follows. And so now, because I take my nu is a finitely supported random walk, and so the random walk entropy is to take the Shannon entropy of the convolution, nth convolution of nu, and divide by n, and take the limit. Okay, so now I'm going to so the proposition 1 is to describe that in our setting, is to prove that in our setting, we can replace the first number entropy by the random walk entropy. So now, let's see. Okay, so before I state the result, so for the rest of the lecture, I would like to fix representation and Anosov representation. So I've fixed Zariski dense. Say rho from gamma in SL3R, okay? So this is my standard assumption. And now, so the first proposition is that, so if I have a random walk, so be finitely supported, so on the Anosov subgroup, and so with the such that the group generated by the support is Zariski dense. So what we can say is that then is unit new station measure mu satisfy. Sorry, I should emphasize that is the one on PR3. So satisfies. So the first number entropy of this measure is exactly the random walk entropy. Okay. Okay, so actually part of the proof has been described in Jalen's talk, but let's just recall and see what the remaining ingredients is. So proof. We consider the action. So here we have two actions. So one is SL3R, so acting on this PR3. And the other one is the action on this flat variety. Of R3. Okay, so this space just consists of the point C, and I have a pair C1, C2, and Ci is an I-dimensional linear subspace in R3. So for this action, so on PR3, we have the unit station measure mu. And now for the action on the flat variety, we also have a unit station measures. Okay, and now I have this projection map, pi. So which is just to map a pair, Ci1, Ci2 to Ci1. Okay. Oh, yeah, thank you very much. Yeah, okay, good. And so now from the uniqueness, we can see, because this pi conjugate this SL3R action, and from the uniqueness of the station measures, we can actually show that now the projection of the station measure on flat variety is exactly mu. So this is the first step. And now we use the fact that this the first number entropy is monotone with respect to the factor map. We have this inequality. So it's the first number entropy on the flat variety is greater or equal than the first number entropy on PR3. Okay, so this is this one. And to continue, I use two facts. So one is that now I consider the support of these station measures on the flat variety, and this. So this is actually the Poisson boundary of the random Wenyu. And second, and I know that now actually because the support of the random walk is in this Anosov subgroup, and which is discrete. And so using these two, and I can conclude that now this entropy is exactly the random walk entropy. Okay. So for this, a reference for this is actually notes by Furman. But it was proved much earlier by this Kamenovich and Vashik or Le Japier. Okay, and now what remains is we want to improve this inequality to equality, okay? And now, now let's take a look at this projection map again. Okay, so let me just do it here. Okay, so I know that on PR3, I already defined the limit set for the Anosov representation. So it's the closure of the attracting fixed point. But similarly, I can define the limit set of the Anosov representation on the flat variety. So roughly speaking, the attracting fixed point is one-dimensional. On the flat variety, I just take the farthest two-dimensional and get a limit set there. And now, and then we can actually show that actually I can restrict the projection on this two limit set. And now I will use a property of Anosov orientation. So and I can show that, let me call the restrictive one this pi tilde. So actually for the restrictive one, it actually has trivial fiber. Okay, and so a consequence of this is that now the pi map is not only a vector map, it's actually measure preserving. So, okay. Okay, let me see. Let me try to first describe in word. Probably it takes a bit more effort because I think now one equivalent definition is that actually now we, for Anosov orientation is that now we actually have a boundary map. So it's from like this PR3, and also times the two plane in R3. It's Grassmannian in R3. Let me use this word. And we have some orthogonality between these two. The starting point is that. Yes, exactly. So basically, I can produce a map from these two, from the boundary to these two product, and also let's say that I have X, and now here I have a one-dimensional subspace, and the other is a two-dimensional subspace, and also using the Anosov property, I can show that if I have two different points, and then this S1 should be orthogonal to Y2. Okay, is it okay? This kind, yeah. No, I think here we really use the property of Anosov orientations. Well, you need this kind of structure. I mean, maybe I want a picture. Okay, yeah, probably I couldn't predict, Is
the spaces are related, dominated, splitting, and so?
Yes, Okay, yeah, okay. So can I just assume this and then finish the proof? Okay,
Yeah.
Okay, sorry. Yeah, it's a bit hard for me to get into yeah. This one? So basically, you consider the cut-down projection. Like, so now, for example, like the one in the first copy, you just take the cut-down, we have this KAK decomposition. And then C1 is that now you find a word, you find so now I have a boundary. So let's say that I have this point, let's say that this S, and then I find a sequence approaching to this S. And then for each gamma n, I do the cut-down decomposition. And then I can take this gamma, this E1, and this limit gives me this C1, this one. And then for the second one, I do the first and decompose with the second. So this will give me the second one. Okay. Okay, and now to continue, once I replace okay, and so now once now I can replace the first number entropy with the random walk entropy. The second step is to construct a free sub-semigroup in a quantitative way. So this is the statement. Okay, so now let's, I need some assumption. So again, my standard assumption is that I'm given an Anosov orientation, gamma to SL3R, so it's Zariski dense. And now I also assume that this group gamma is torsion-free, and I fix a set of symmetric generator S in the group, and I will use the word matrix given by this set of generators. Okay, so this is the statement of the theorem. So again, is to construct a free sub-semigroup in a quantitative way. And now let me walk you through the statement of the theorem. So it says that now I can find a finite subset in the group with cardinality greater or equal than 3, and some constant C1, C2, and L0, and some constant M, such that we have the following. So the point is that now, first I have a set F, and then the second input is that now you give me any set, you give me any annulars AL. So these are the set of words with length L, and any subset S in these annulars. And now I can find a large subset S prime in this S with large cardinality. So the cardinality of S prime is greater or equal than this some constant and cardinality of S. And also, let me try to draw a cartoon to guide you through. So the point is that here I have a finite subset F, and now I have another set S. And now I want to find, in these two, I both want to find some large subset. And such that once I use these two large subsets, so what happened is that now, the first is about getting a Zariski dense sub-semigroup. So I use the word rho F. So F is from this F prime, so I do rho F to the M. So this one will give me a Zariski dense semigroup. And now the second one is to using these two subsets to construct free subgroup. So the word I'm going to use, is this kind of word. So you can see I take some S from here, and then I also put some word F in the other way. I do this kind of combination. So using this kind of combination allows me to freely generate a free group. So, Okay, so I couldn't just use elements in one subset. I need to do some combination in order to get a free group. And now the third property is that now, once I use this kind of word, actually the length of the product of the word is almost the sum of each word. This is okay, and so these are the statement, and so this is the picture. Now here I try to draw a cartoon to help you understand what's happening. Again, I have two subsets, F and S, and now in these two subsets, I found two large subsets, S prime and F prime. And then the word I'm going to use is first do some S and then F. So the secret here is that hopefully hopefully this will give you. I want to emphasize the secret here is that to get these two to produce a free group, the pattern I want is that when we have these two geodesics, OSO and OFO, I want these two geodesics have large angle. Okay, so once I have, this is the secret sauce that goes into the proof, and once I have this large angle, and then using this as a building block, I can expect that I can get a quasi-geodesic. Okay, and so this angle is what's described using this Gromov product. It's a quasi-geodesic, so which means that it's almost a geodesic. In the word metric, yeah. Okay, so at the moment, my plan is that I would just state this theorem and then also give you this picture. And now what I'm going to do is that because this is a dynamics summer school, so it's not a geometric group theory summer school. So I should switch the order. So I will assume this geometric group theory input and see how to use it to compute the random wall entropy and the Lyapunov exponents. Okay, so I want to just keep this theorem statement up, and also I want this picture. Okay. Okay, so now when it comes, I need to introduce three notions when it comes to computing the random wall entropies and this Lyapunov exponents. So now comes to step 3, and now I let this A to be a Cartan algebra in SL3R. So it just consists of the diagonal matrix lambda. So diagonal lambda 1, lambda 2, lambda 3. So lambda I is in R, and also the sum of lambda I is 0. So this is a Cartan algebra of the Lie algebra of SL3R. Okay, and now we take a positive Y chamber. So it consists of the diagonal matrix such that lambda 1 is greater or equal than lambda 2, greater or equal than lambda 3. So Y chamber. And so now let A plus be the exponential of A plus, and let K be SO31. And so now I pick any group G in this SL3R. So I know that it has a Cartan decomposition. So which is to write G in this product, G, KG, AG, and KG. Let's say that this is KG tilde. And which is, so K tilde, Kg tilde and Kg is in K, and A is in A plus. And so actually this AG is just the diagonal group of the singular values. And so now I also do a Cartan projection of G. So let's use the Cartan G, so which is to read the corresponding elements in the Lie algebra. So I read this lot, so this is the diagonal log sigma 1 G. Okay, and so another notion is called the positive functional on A. So say psi is a linear function on A. So it's called positive. If this function is a linear combination of the simple roots. So psi is this A1 alpha 1 plus A2 alpha 2. So with this alpha 1 alpha 2 greater or equal than 0, but not all 0. And this alpha I is the simple rule, is to take the, so when I input a vector lambda, so I just read lambda 1 minus lambda 2. Okay, so this is the statement when it comes to using this, this is the statement when it comes to using this large free subgroup to compute the random wall entropy and the Lyapunov exponents. So I let psi be a positive function. Function on A. And I assume that I get a divergent series. So more precisely, in psi, I just input the Cartan projection of the group element. And take minus, and take exponential. And now take the sum, gamma in gamma. So this diverge. And the consequence is that now I can find some constant such that the following holds. So, if you give me any epsilon, and I can find infinitely many n and finally supported measure. On the group, such that, so the first one is that now when I use the support of this measure on the group and use it to generate a group, and so it actually is Zariski dense in SL3R. Okay. And the second statement is that now when I now I consider the difference of the Lyapunov exponents. So this lambda p nu minus lambda p plus 1 nu. So its difference is in this scale, say Cn. So for p in 1 and 2. And now the third one is about the controlling of the random wall entropy and the Lyapunov Lyapunov exponents. So is the random wall entropy of nu is greater or equal than 1 minus epsilon to the n. And now when I input the Lyapunov vectors of the random wall to this functional, is actually is controlled about by 1 plus epsilon to the n. Sorry, which line? 2 is that I'm comparing p and p plus 1. Yeah, I'm comparing the difference of these two Lyapunov exponents. So the difference is in this scale. How C play in? Sorry, which C? Psi. So you are, what question about Kasai you concern? Oh, okay. Last one, sorry. Yeah, it's good. Okay. Okay. So this is about the quantitative way to control the random wall entropy and the Lyapunov exponents. Okay. Okay. Go ahead. So it's free. So it's free. This is to input the Lyapunov vectors of the random wall into this functional. Yes, exactly. Okay. Any other questions about clarification needed for the proposition? So I think in general, actually, sorry, I forgot that. I think I forgot to mention the history of this variational principle. So actually, for us, we prove for the Anosov this what's called the Borel-Anosov orientation in SLNR. And later, Lejapier and Lessa proved this statement for this K-Anosov orientations. And there are other variational principles. For example, for this IFS, it's proved by Maurice Schumacher and this Maurice Sert. Okay, so now let's just take about hopefully I can finish in about 12 minutes. Just try to finish this, the proof of this proposition, and then it takes about 12 minutes, and then you will see how it leads to our variational principle. So let's do some technical work. So proof. So now, to prove this proposition, I use the existence of this large free subgroup. Okay. So now I'm going to apply this proposition to my gamma, and I know that first of all I have a set F. So so then so with the cardinality of F greater or equal than 3, and also I have some constants, say C1, C2, L0, and some M. Okay, so now the first step is to try to figure out what the annular should be. And so I know that what I'm given is a divergent series. So since let's call this divergent series 1. So since 1 diverge, so I'm going to consider this set as 1. So it just consists of the word gamma, such that when I just input the Cartan projection of rho gamma into this functional, it requires less or equal than n. I know that I can find infinite many n so such that this set S1 so has cardinality greater or equal than, because here for the exponent I use e to the n, so then diverge, it means that it has the cardinality 1 minus epsilon to the n, okay? And so at the moment what I get is probably something of large cardinality, but it's of the not very good shape. And to continue, because again, what I want is an annular. I want to cut out an annular in this kind of like large set. And so one observation is that because this psi is a linear combination of these simple roots. In particular, I know that one pair of simple roots, the coefficient should be not 0. And so when I input the Cartan projection, and I know that I can find some pair of the simple root, say P in between 1 and 2, and some constant C in between 0 and 1. So now, this constant C, attention is that it's going to change line by line. I'm not going to keep track of the constant C. So I know that one coefficient is greater or equal than 0, so it should be C and some, say, sigma input log P minus this log sigma P plus 1. And now input the word is rho gamma and rho gamma, okay? And from here, I know that I can use the property of this Anosov orientation. So the ratio of the singular value grow exponentially with respect to the word length. But now I take the log, I know that it's greater or equal than some constant C and the word length. So consequence, now this S1, because for the elements in S1, I have the upper bound on n, and now I know that S1 consists in the ball. The word length is less or equal than C to the minus 1 and capital N. Okay, good. So this is how I cut out a large ball. And now, at the same time, I also want to cut out sort of a small ball here. So I use some soft estimate. So now I want to let's consider a small ball. So let's say that I consider gamma. And so the word length of gamma is controlled by some constant, small constant C times n. So C is something in between 0 and 1 to be determined. Okay, and so the point is that I want this, the cardinality in the annulus large, so I want an upper bound. And so a soft way to estimate this, I know that I can just use like the cardinality of the generator raised to power C to the n. So this is e to the C to the n logged cardinality of S. So a choice of C can be 1 over 2 logged this one. And once I have this, I have e to the n over 2, which is less or equal than e to the 1 minus, let's say that this is epsilon to the n. Okay. So sorry, here I should make a remark is that now this large annulus, so the cardinality, because it contains S1, the cardinality is greater or equal than e to the 1 minus epsilon to the n. Okay. And so now I can cut off of an annulus because the large ball has large cardinality, and the small ball has a small cardinality, and then I know that I can find some L in between these two numbers. And see such that now this S2 just consists of the word. And so the word of length L sorry, probably here I want not just epsilon, probably I want something a little bit more, and let's do, but you know this is n over 2, this is n, so I can just shrink something, okay? This epsilon is not the same as this epsilon, but then the point is that this is large, this is small. I know that in between, I can find some L such that the cardinality of S2 is greater or equal than e to the 1 minus epsilon to the n, and the number in between C inverse L and C inverse n and Cn, so which is this one. So it's okay, good. So I have an annulus. Okay, and so now once I have an annulus, I will keep applying the construction of large free subgroup to this S2, this annulus. And so I just copy and paste what I get. I know that now by this proposition 2, I can find a large subset in the annulus and this F prime in this F. So the cardinality of this S3 is just some proportion of this annulus and this cardinal. Oh, okay. Sorry? Oh, yeah, that's a definition of S2. Let me see. Sorry. Yeah. So actually, I can do this because this is a sphere. What's the question? I don't. Okay. Yeah. Sorry. Yeah. I just S2 is a sphere, but I think in our paper we call this kind of set an annulus. So that's why I just keep using these two words in the, okay. Yeah, I'm sorry. Okay, good. And now I'm going to apply this proposition to this S2, and so I just write out what I get. I know that I can find a large subset here. So in terms of cardinality, and also an F prime in my finite subset. So with F prime is the cardinality minus 2, and such that now I just to construct the free group, I use S free and this F prime. So I do this kind of pair. So SF zeta. So S is in S free. And this F is in F prime. Zeta is the multiple M and 2M. So this one freely generates a free group. Okay, good. And I think it's good to pause a little bit to ask ourselves what should be the cardinality of this S tilde. I know that this S tilde is constructed using S free and F prime. I know that its cardinality should be greater or equal than this S free. But now S free is a large subset in S2, so it's greater or equal than C1 inverse S2. But now the cardinality of S2 is this e to the is some e to the 1 minus 2 epsilon over n. And so this estimate is useful because what I'm going to do is I'm letting this nu be the uniform measure on this rho as tilde, okay? And so now, to compute the random walk entropy of this uniform measure, I know that it just equals the cardinality of this S tilde, and which is greater or equal than this 1 minus 2 epsilon to the n. So this is the first estimate. And also this is the first part of this equation 3. And now I need to, now I have this uniform measure. I want to check these three properties. And so we call that, so proposition 2 tells me if I use the word rho f to the m, it gives me a Zariski dense free subgroup. And now this rho fm is, rho fm can comes from this S tilde in this way. So I just do this rho SFM inverse and rho SF to M. So I get rho F to the M. But now this product, I know that is in the support of the random wall. So hence, so this group generated by the support is Zariski dense. So this finished the first property. And now comes to the second one. So the second one is the control of the Lyapunov exponent. So this one is, if you are familiar with the definition of the Anosov orientation, this one should be not that hard. So I know that Anosov orientation it means that I have a gap between the first and second singular value, right? And then the Lyapunov exponent is to take the log and do the average. So that's why we have a gap. Okay, let me just write down. And so by the of this Anosov representation, and I know that for any p in 1 and 2 and any gamma, and so we compare log of the p singular value minus log of the p plus 1 singular value. Input the word, and it's greater or equal than c, controlled by the word length. And so once I have once we have this, and now I know that. So now this lambda p nu minus lambda p plus 1 nu, so is by definition is the limit as k goes to infinity 1 over k, and this log, and this is sigma p and rho gamma, and minus log sigma p plus 1 and rho gamma. Okay, sorry, I lied a little bit because now here I need to estimate the word length of gamma. And so I'm going to do it, and together with the remaining part of this free. So in free, I also need to estimate what happened when I input the Lyapunov vectors into this functional. Okay, and so the observation to finish the proof of 2 and 3. So I need the following estimate. So actually it's a lemma by this Bocci and this Porti and Sambarino. Okay, so in 19. So it's about the subadditive of the singular values. So again, I'm going to just restrict myself to the Anosov orientation in SL3R. So once we have this, and so we have the subadditivity of the singular values. So we have some delta, and such that you give, we have pick any three numbers, L and K and M. So we have, so now the P singular value of the word, say gamma 1 and gamma M. So it's actually bonded below by these two products, say delta, and this is rho, this is sigma P, and I use gamma 1 and gamma K, and this sigma P, and rho, gamma K plus 1, and gamma M. Okay, so this is one side, and the other side is that now this rho, gamma 1 and gamma M is bonded about by delta and sigma P plus 1, and rho, gamma 1, gamma K, and sigma P plus 1, rho, and gamma M, gamma K plus 1, and gamma M. Okay? Okay. So probably, I guess I gradually lose you on the computation. But let me try to give you a hint on to guide which hopefully will guide you to finish the proof. Again, the observation is that now the free group I generate use this two combination. One is S, and the other is F zeta. So S is in this S3, and this F is in F prime. Zeta is M, and this 2M. Okay? And so the point is that for this S3, I know several properties. One is that I know that the word here has the word length. Now I know the word length greater or equal than some constant times n. Because if you remember the picture, I have a large ball and a small ball. I cut out a sphere in between, so I have this control. And also I know that this S3, because it originally comes from a S1, but an important property of this S1 is that I know that when I input the Cartan projection to the functional, is less or equal than capital N. Okay, and now when it comes to computing this Lyapunov vectors, what the input is the random walk. Is somewhere like this S1 tilde dot SK tilde. And more precisely is this S1 from S3 and F1 zeta 1 dot S2 SK and FK zeta K, right? And now the point is that now I use the subadditivity use the subadditivity to control the singular values. And also, I know that the arrow, now use subadditivity to control S. And then the arrow is F, but this is a finite set, so it's within the error range. So that's the proof for this one. I still have one part, but you can ask me in the Q&A session.
Questions or comments? If not, let's advance. Sorry.
In the statement of variational principle, psi does not appear, so how do you select psi to prove variational principle from this?
Oh, okay, so let me just finish the last bit. I just need 3 minutes. Okay, it's just an observation, So, so now we call, what I want is to approach this Lyapunov dimension below by the affinity exponent. So this is the definition of the affinity exponent. So let me do it in an exponentially fast way. So, no, I think it will be a little bit pity because I spent so much effort doing the computation, but we couldn't get a conclusion. And so now what I'm going to do is that I'm going to rewrite rewrite the definition of this affinity exponent. So basically, I use this functional. You give me any s in between 0, 2. I have this psi s. So this is the thing I'm going to apply this proposition free. So it's S3R to R. So now you give me any g, so I do this formula. So I in between 1 and the floor, and this log sigma 1 minus this log sigma I plus 1, okay? And plus this s minus the floor, and this is log sigma 1 minus log sigma the floor plus 2, okay? So we write this. And now let's do another variation of this formula. As you can see, this is a linear combination. So it turns out that I can do a linear combination, say this A1, 2, this is log sigma 1 minus log sigma 2, plus this A1, 3, this log sigma 1 minus log sigma 3. And I just do the Aij in between 0, 1, and the sum of Aij is s. So do this rewriting, and then you can also rewrite that definition of the Lyapunov exponent using this kind of linear combination. And that once you do this rewriting and just apply this proposition, you will find why we have how to use this gap.
Thank you. I think that we don't have more time for more questions because we need to make the photo. Let's thank again the speaker.